of people online, and only 20 actually showed up for what was quite an important conference. And it's good to see that things are getting bigger and people are becoming more confident about taking part in conferences. And of course, the important thing about conferences is the serendipitous nature of encounters, talking over a poster, chatting over a paper during the coffee break. Now, I'm Mark Pearce, and together with Stephen Harding and Chaz Jones, we sort of brought this meeting together. Quite an important meeting because it's a collaboration between the Royal Society of Chemistry and the Society of Antiquaries. Now, we're going to now listen to two official welcomes. First from the Royal Society of Chemistry, because Steve Harding is a former chair of the Chemistry Biotechnology Group and is Professor of Applied Biochemistry at Nottingham, where I work. And then we'll hear from Martin Millett, who's Lawrence Professor of Classics at Cambridge and who's the President of the Council of the Society of Antiquaries. So Steve, since we're in the RSC, perhaps you ought to speak first.
Thank you, Mark. Yeah, thanks, Mark, and welcome from me and also the Royal Society of Chemistry and the RSC Biotech Group, who are hosting this meeting jointly with the Society of Antiquaries. And I think this is the first time that the two courtyard societies, the Courtyard Societies was all in Burlington House. So even though Antiquaries are 10 meters away across, it has taken us this long to do something together, which is remarkable. It doesn't mean to say there's been no interaction between our two societies in those years, and there was one distinguished chap, J.D. Bullock, whose picture is there. He was a professor of chemistry at the University of Manchester and an expert on fermentation biotechnology. But he was also active in the field of archaeology in the northwest. So this chap, you couldn't find two diametrically opposed books. Pre-Conquest Cheshire 383-1066 and Biosynthesis and Microbial Development, which meant that somebody asked them the question once, do you know D. Bullock, who's at Manchester? I'm actually the same person. And Bullock was the first chairman of the biotechnology group, so he's a person very close to me. And you know, I'm a chemist, a physical biochemist, but I've got also an interest in antiquaries, especially in the northwest. And one of my interests is the Battle of Brunanburh, some famous battle was fought in AD 937, and still people debate where it is, and perhaps isotopes are going to help us to solve this. And we've got a nice collaboration going on at the moment with groups in France and Norway. So the difference between Bullock's time and our time is that now, although these topics seem to be so far apart, these subjects are coming together to crack important problems. So it's great that we have a very diverse audience, and also a special welcome to those joining us online from places as far field as Newfoundland, Natal, East Berwickshire. We've got a special welcome to people from the University of the Third Age who are also joining us. And as Mark said, we're into the world of hybrid now. We've come through some sort of black hole out the other side, and this is just how it is now. But yeah, for the online people, it's a shame you can't be here, because this is a wonderful environment to have a scientific meeting. So hope you enjoy the meeting. As Mark said, it's got a real purpose to try and stimulate the growth of databases, so we can provenance ancient objects and also people, and solve important questions in terms of movements of peoples, locations of battles and things like that. So I'm looking forward very much to this meeting. And Mark, hand back to you, shall I? Martin.
Your second, third welcome comes from me as president of the Society of Antiquaries. We're just across the courtyard from Royal Society of Chemistry, and as Steve said, it's time that we work more closely together as the societies in the courtyard. I just want to say a couple of things. Firstly, the Antiquaries, as those of you who work on the archaeological side of things will be aware, it's a very old established society founded in 1707 for the study of the material past. The study of the material past is in many ways interdisciplinary, and in that sense the proceedings of today's meeting really fit in with a tradition of study that goes back over more than 300 years of using a wide variety of approaches to understand people and the things they used in the past. Second point I would like to make is that that interdisciplinary collaboration really lies behind the foundation of the courtyard here. Courtyard's occupied by this Society, Royal Society of Chemistry, the Society of Antiquaries, the Linnean Society, Astronomical Society, and Geological Society, all of whom are passionately and deeply engaged in discovery in science and humanities. The bringing these societies together in the courtyard was a Victorian idea brought about in the 1860s when our Society of the Antiquaries and the Royal Society were relocated from Somerset House, which we had occupied since the 1770s. We were removed from Somerset House as the inland revenue grew in size, and the Somerset House was required for the tax office. We moved here slightly under protest, but to fulfill that Victorian idea of a cultural campus. And as we campaign with government over their requirements to pay astronomical rents for this courtyard, we should remember and celebrate that Victorian ideal of arts and sciences coming together in a cultural campus. And that really brings me to the theme of today's meeting, which is work on isotope research, which is clearly an area where our two societies come together in our interests. Now, as someone who works on the Roman world, I have admired and watched the work on isotopes developing in the last 20 years or so. It's a fascinating and absolutely central subject in archaeology now. And it's an area where there are clear commonalities of interest between chemists and archaeologists in getting the standards and the methods refined. We go through these processes in archaeology of finding new methods, experimenting with them, being over-optimistic about them, and then over-pessimistic about them, and then we come to a central view. My suspicion with isotopes is that we're at the stage where we went through the optimism, we're now, oh God, it's more complicated than we thought. And this meeting is absolutely central to bringing us back to that balance of interests and working together to understand this. So I very much welcome the collaboration between your society and ours for this, what looks like a fascinating programme. I'm only sorry myself that I have appointments this afternoon, which means I can only be here with you until lunch. But I very much look forward to this, and I think we've got an excellent, brilliant programme put together by your organisers, so well done to them. I very much look forward to seeing how this develops. Thank you.
So just a quick practical things. There are three purposes to this conference. One is to bring together people who work on different isotopes, and that's very important because often people work in silos. Second thing we want to do is hear about latest research, state of the art. And then the third thing, which is here on the slide, is, and as Martin and Steve have both pointed out, is to make people think about data availability, data sharing, data quality. We initially proposed this conference before lockdown, and we had to cancel it twice. And in that time, there have been some very important developments. And one of them is the proposal from Sabine Klein's group in Bochum for a lead isotope, a new lead isotope database. And in fact, we're going to hear about that later on in the program. So today, there's quite a different range of isotopes that are going to be discussed. And I think that without further ado, I'd like to pass over to Jane Evans from the Geological Survey. She's also a special professor at the University of Nottingham, who's going to talk to us about all models are wrong, but some are useful. Construction and use of spatially distributed multi-isotope datasets. Over to you, Jane.
Am I controlling this or are you?
I want to get the link open now.
Okay, let's do that. Okay, thank you very much for inviting me. And this is a quote by statistician George Box that I think is very well worth keeping in mind when we start to think about larger data sets, how we apply them, multi-isotope systems. Because, as I want to show you, models are very useful, but you have to understand the limitations of how they're constructed. And so, to do that, what I want to show you is this website that the BGS hosts. Oh, now, right. Here we go. Why am I not on there? Take down the, minimize that. Close it. Yep. Okay. This is a website that we developed in 2018. And it came about really as I found it increasingly difficult to describe overlapping spatially distributed data sets of increasing numbers of isotope systems. And so we set out primarily with the aim of trying to understand human migration in Britain to make this, I hope, user-friendly system. And what you can do is you can enter data for strontium and oxygen and sulfur. And what this does is so you put in a strontium value, and what you get highlighted in orange is those areas that you cannot exclude as, let's say, an origin for that value. You can superimpose on that an oxygen value in most forms that you want. I'm going to try We reduce it again. And if you happen to have sulfur, you could perhaps add in the value of 12, if that's what you measured. And you end up, there you go, with a map of the areas that you cannot exclude as the origin for the isotope composition of the tooth you're looking at. Simples? Yes and no. That's where the model's good, but let's think about the constraints and how this is built up. And in a way, this is what I want to take you through, are how we've constructed these layers and the limitations and the benefits. And as well, this website was set up in 2018, and I'm about to upgrade it significantly. And some of the data I've got, while it's not on this website, hopefully it will be up by summer. So there we are. That's the simple option. And now we want to look at the reality. And the first thing you have to think of, I think, in isotopes are the number of constraining issues when you're trying to accrue data. It's costly. A strontium analysis costs 200 pounds. So it's not easy to gather sufficient data to get a statistically viable data set for contouring, for instance, over a large area. It's going to cost a lot. You have to think at your sampling strategy. When it comes to archaeology, what samples are available? And then what uncertainties have you got? And how do you display the data? So, first of all, I want to talk about the strontium isotope layer in this. Now, this layer is a domain-based map, and I'll explain that a little later on. But number one to note is that while we've designed this website for human interpretation, it's based on plants. And the reason we've chosen to work largely with plants is that they are ubiquitous, they're free, you can collect them anywhere, they're moderately easy to handle in the laboratory. But obviously you're not matching like with like. The data density that we now have is moderate. And we've based the data distribution on geological domains because basically strontium isotopes in the biosphere are quite strongly related to the underlying geological much of the area. And we're talking about £600,000 worth of data. Now, this is the new data, which isn't on the website. But what you've got is, as you can see, if you're familiar at all with the geological map of Britain. Thing? Don't look at it. Anyway, you can sort of see that we've structured the domains, which are in different colours, based on the geology. Now, the one in the middle, the median, is the colouring up of the average values. Because what we do is we go out, we collect a lot of samples. Let's say we've collected samples all over the chalk. You then take that data, you average, or you take the median value and an uncertainty range, sigma, 1 sigma, 2 sigma, interquartile range, and you allocate that value to that domain. So the map in the middle gives you the median value. The lower and upper quartiles, the 50%, show you the data range that would light up on the map if you were searching at the moment. And then the end ones are the extreme ranges of the data set for those domains if you were to use 90% of the data. And this, again, is an important issue because one plant does not equal 3 years of precipitation of a human tooth, let's say an M3. We can't directly equate the range of data that we find in plants with the range of data that we find perhaps in human teeth. And to the best of our ability, these are the full data sets some years back for all the human enamel that we found in Britain versus all the plant data. And basically the plant data is far more dispersed. And broadly speaking, I would say that the human enamel is reflected in the central 50% of the plant data, okay? So because of that, when I established the ranges on the website, I set it to respond only to the central 50% of the plant data, because that equated to human data. But as time's gone on, for instance, people are using these data sets for more than just human data. I mean, what happens, for instance, if you were asked to look at the strontium isotopes of a wooden beam in an old church? You would then be comparing plant data to plant data. You might want to use the full data set. But equally, supposing you're looking at a slice of enamel from a horse's tooth, which maybe was precipitated within a month, and maybe the animal was in a single field, then again, perhaps you might be wanting to look at a wider set of data than is the 50% that we've defined as the best estimate for human data. So you have to know how and why that website is responding to your data and your question, and you have to really frame what you're looking at in terms of understanding what the website is returning to you. And this is what happens, for instance, if you entered the data of 0.710 in the current data set, the map would light up like that because it's reflecting the central interquartile range of data there, responding to the sort of best estimate for human values. But if you enter it at the 90% level, you'll see that the coverage is much greater. And this hopefully will now be incorporated in the new website, that you'll have the option to use the interquartile range, or essentially the full data set minus the extreme outliers. And that means that you need, again, to think about what you're looking for and how you're addressing the data set. This theme of the relationship between the data that's used and the way it's interpreted extends to drinking water. Now, in Britain, we're very lucky. In 2003, George Darling produced a map of oxygen isotope compositions for drinking water in Britain. Fairly good data density, and he contoured it at 1 per mil levels, which was absolutely fine based on the data he'd got for water. We took that map and we converted it into an interrogatable version, which is on the website. Now, in order to compare human tooth enamel to drinking water, you first of all have to convert it using an equation, and there is uncertainty in that. There are 2 or 3 equations that are used, so you've got uncertainty inherent in your conversion. But more to the point, it's become apparent that human populations don't have limited ranges of 1 per mil. At best, they're probably 2 per mil and possibly 3 per mil. So the contouring on the drinking water that was legitimate for the original values is not really legitimate for the interpretation. It's overly precise for the requirements of human enamel. And to that end, I took another approach, which was to look at human enamel from data sets where we were as convinced as we could be that the data was local, either because we had burial records or they had unusual chemical attributes, for instance, the individuals from the Outer Hebrides, that we could be fairly certain placed them in that area. And what I did was then take the mean and standard deviation of populations on the west and south coast, where the drinking waters are at their highest value, and the remainder on the eastern coast, and I simply split Britain into 2 domains for the purposes of looking at oxygen isotopes in teeth. And again, these are triggered at the 1 sigma level, because these 2 populations are distinguishable at the 1 sigma level. But my suspicion is that at the 2 sigma level, at the 95% confidence limit, there would be a massive overlap, and basically there would be very little except the extreme outliers that would show up. So again, you have to be aware that when you reject a location on the basis of human oxygen, you're doing it at the 1 sigma level. Okay? I don't know whether to incorporate I don't think I'm going to update the oxygen at the moment. I'm struggling enough with all the other things I've got to do with it. Now, the third isotope that was in the original map was sulfur. And at that point, 2018, we had a very restricted data set for sulfur. And the main use of sulfur really is that seawater has a very distinctive sulfur isotope composition of about plus 20. And the most common use of looking at sulfur in collagen is to argue whether or not you can see a marine influence in the collagen. In other words, are you seeing elevated marine values or not? And so sulfur, again, the data was based on plants because that's how we can be sure that it's spatially correct. We had restricted data. One of the things my colleague did was she did traverses from the coast inland on the west coast and the east coast. And what she could see was the drop-off from marine values of about plus 20 to within below, I think it's below 8, 15 kilometers on the west coast and within 10 kilometers on the east coast. So unsurprisingly, it looked like there was a greater influence of marine conditions on the west, where the weather's coming from the west than the east. And so we constructed this preliminary map and put the marine influence around the coast. We saw it. We had some data which we called other substrates, and then on a couple of substrates, we thought we got enough data maybe to allocate them a value, and we put the chalk in. But what we did notice was that we were getting some negative values that seemed to be plotting within the Jurassic clays. That's the brown data. Now, the problem with that is that modern pollution tends to contribute negative values. And up until this study, I think it was common to assume that if you got a negative sulfur value, you probably had a polluted sample. But this correlation between the lower values and the Jurassic outcrop suggested that maybe there was something else going on. And so we managed to get together a new grant called Wet Feet to look at sulfur isotopes, particularly in this area of the Jurassic muds. But at the same time, we had quite a lot of samples from Britain that we were able to do to extend the mapping. And we came up with this map. And what I would say is, before we put this map together, what we did was collaborate with the Rothamsted Centre, which has plant samples from the 1800s on an annual basis through to the modern day. And we analysed and reanalyzed this sequence, and we could show that whereas in the 60s and 70s there was a strong pollutant peak, at the point of the Clean Air Act, this dropped off, and we're now in a situation where sulfur and lead pretty much seem to be showing up pretty close to pre-pollution values. So we feel fairly confident that the sulfur values that we're mapping here are genuine biosphere-derived values. Now, what we've got here in particular, I think this map shows up a number of primary features. First of all, I'd have to say slightly surprising, but maybe not, Scotland shows a much stronger marine influence than the rest of the country, and I guess is battered with more westerly derived, clearly a strong coastal signature on the west coast. Those marine influences show up very well again in estuary areas and on the extreme west coast of Britain and Wales, England and Wales. What we also see is the clear influence of the Jurassic in this area, generating negative values. Now, again, I think this is interesting to come back to rights and wrongs. Because we contour mapped this, the data that gives you those negative values is kind of spilling out beyond the Jurassic muds, whereas in reality, I think these negative values will be restricted to the Jurassic muds. And the reason that we think that we have these negative values is the Jurassic, not only is it actually an anaerobic environment geologically, but it's a thick clay that supports the waterlogged areas such as the Somerset Levels and up around Peterborough. And so we think that it supports anaerobic and waterlogged soil conditions. And these are the conditions in which the sulfur is bacteriologically sort of being reduced. And that's why you have this association of the negative values overlying the Jurassic. Now, again, I think the broad scale variation of this is legitimate, but if you were to take an analysis of a human collagen and type it in, to what extent would there be very local variability? If sulfur is dependent on hydrogeological conditions, then you could get quite a diversity within a small area. And again, we come back to the effect. Do we understand the difference between measured values in plants and how that translates exactly into human data? So at this point, I think this is a good map of plant values. But again, using it for humans, it should be, and animals, it should be clearly taken with the uncertainties that go with the data distribution and the interaction between the animals as they sample the biosphere. Now, the final map that I've been putting together is a lead map, lead isotopes. And I've done this by, there's a fantastic paper by Yanni Blikatov and others in 2016 where they compiled, I think, all the lead isotope data on lead deposits, galena deposits in Europe. There's about 9,000 data points and about 700 from Britain. And I've added some to that. We were interested in whether lead in particular could be used to distinguish between major tectonic units in Britain, because Scotland is underlain and is geologically totally different from England and Wales. They were once miles apart with an ocean between them. And we know geologically that the lead isotopes from Scotland are very different from those in England and Wales. Now, let me say now that we obviously clearly have lead pollution issues. And so this can only really be used in pre-mining areas, or if one is confident that the sample you're analysing is unpolluted. And to that end, the best estimate you can do on that possibly is to make sure that the concentrations, if it's in a human enamel sample, are below the threshold that's considered to be pollutant, indication of pollutants. But what we've done here, what you see is, as far as Scotland goes, this absolutely, excuse me, it's not my data, so I can say this, absolutely fantastic zonation, which shows the sloping down of the ancient Canadian Laurentian shield under Scotland. It's sloping in and down. So at the Outer Hebrides, it's exposed and you're directly sampling it. And then it dips down under Scotland, providing geological layering that's very clear in the mineral deposits in this area. You then come south, and basically England pretty much has one lead mineralization event, which is, again, as we geologists call the Hercynian, and it's where the mineralization in southwest England and the Pennines occur. And in Wales, there is somewhat earlier mineralization, and so Wales pulls out as slightly different again. So you've got these major domains in terms of mineral composition. It is basically England, Scotland, and Wales. And then from an archaeological perspective, and I don't know if you can see in red, I've outlined the chalk. I feel that the chalk is an important factor in archaeological studies. And so we've tried to get a characterization of the lead. Now, there's no mineralization of chalk. So there's no mineralization in chalk. So what we've done is taken the fairly restricted numbers, and predominantly those of Janet's PhD, to look at the lead isotope compositions of chalk as another control factor. And you can see there the distribution. This is the published data. Now, to go on and justify, I haven't actually incorporated the fact that what I'm trying to do now is I'm trying to demonstrate that the biosphere samples that we have are consistent with the mineralization values. But again, the problem is very little data, and particularly from Scotland. Well, from actually, to be honest, from everywhere. What I'm trying to find is lead isotope data on pre-pollutant or unpolluted archaeological samples of known provenance to show that we can create a, let's say, Welsh mineralization field and show that biological samples plot in the same field. But that's kind of where we are at the moment. However, just to summarize, by combining the various data sets, we provide means of a multi-isotope exclusion of possible sites of origin. That's what we're aspiring to do. But in doing that, you must appreciate that you need to cite the limiting factors and you need to understand the underlying principles of the construction and what it was built for. And for instance, I've just remembered what I was going to say about oxygen, which is the oxygen map cannot be used for animals because oxygen is species dependent and all the data is for human data. So again, little things like that that I find people misusing it or misunderstanding it for. So I'm hoping that that sets the scene for, it's great to have huge data sets. It's very important to concatenate these things and to be able to compare. But when you then use them, be aware of all the information that you may not be seeing in the original publications that tell you about how, where, and what this data was collected. Thank you very much. Oh, yeah.
We've got time for one or two questions, and if there are any online questions, we can take those as well. So just one or two before we move on. Does anybody want to shoot a question at Jane? Or should we wait for the discussion? It's up to you, really.
Or grab me a coffee.
Or grab her over lunch, yes.
Okay, this program you just type in, is that set up for biological origin?
Well, this is the issue. At the moment, it's fine for plants because it's based on plants. It's set up, as I say, to focus in on relating human enamel to plant data, but it's there. And the new version, hopefully, will give you access to, I mean, it's really only the strontium one where I've made a decision about the limits. The rest of it is based on a contouring system. And what we're working on, I haven't got yet, is the uncertainty envelopes that I want to publish alongside, say, the sulfur map. And we're just working on those at the moment so that you can see, you know, what the uncertainty is in certain areas, because obviously the data density varies and that controls the uncertainty levels.
Zoom cannot hear the questions from the audience.
Okay.
So we need to speak up, and perhaps you could just repeat that question and summarize for this time.
Yes. Should do it by the microphone.
You could, yeah.
Yeah, apologies to the Zoom crowd. The question was: does the sort of the program that Jane explained near the start of the talk, was that applicable not just to biological samples but also to general samples? Yeah.
Well, within the limitations of how you use it, I mean, that data is there. And if you feel it's appropriate to the subject you're doing, then yes, the program is up there, openly available. All the data is open source and up there with it. So not only can you use the website, but you can download all the data and use it, frankly, as you wish. So if anybody basically wants to know about other things that can be used or other applications, come and see me.
That's fantastic. Thank you. Thank you, Jane, for that cautionary introduction to our work for this morning. So it's now over to Till Sonnemann from the Otto-Friedrich-Universität Bamberg, who's going to talk to us about isotopes, isoscapes, and the search for geographic origins, unrealized potential or unrealistic expectations. I think it sounds it's going to be more or less on the same cautionary theme. Thank you, Till.
Well, thank you very much for the kind introduction and the invitation as well. I mean, I've been very happy. Well, I'm very happy that we can actually have it here in this conference on site in London. Thomas Meyer, a German archaeologist, said at a talk, and I'm going to quote him: in England or British people tend to start a talk with a joke, in German, we start with an apology. And my apology today is about, firstly, I'm not going to talk about this time frame of prehistory to Viking Age. And the other thing is, actually, this work has been done together with Jason Laffoon, who really is the specialist on isotopes. I'm the mapper, or I'm the, I could say the GIS guy who is putting the maps, manipulating the maps that we can see something on it. I hope I can answer you some questions afterwards on this, but some will probably better be answered by him. And Jane has already brought up a lot of these issues that I'm going to talk about, and maybe answered some that we have been struggling with. So you saw already, we're talking about paleomobility and human migrations. So it's going to be an add-on pretty much to the talk that we just saw. And the question is, how reliable are those isoscapes that Jane already showed now in a different region? Because we have this issue that we have often regional maps. We don't have the global data. Even for regions, we have this problem that we have very limited samples, like firstly plant samples, human samples, animal samples. And most of this work we've been doing was within an ERC by Corinne Hoffman. We've been working in the Caribbean. So I stick with this map pretty much. So you all know the Caribbean. You can probably orientate yourself quite easily here. You see the data that we've been using previously. That was in a paper that we published 2017 on 3 different samples from Trinidad, Cuba, and Caracas, and I'm going to speak about them as well. We started with Puerto Rico with an animal tooth and put in recently more modern data to actually check what we actually got in these, what kind of maps we actually created there. So just quickly, you are all, most of you are chemists, I understand. So I don't really have to go through this in detail. But we're looking at regarding strontium on a strontium 87 to 86 ratio, and this strontium 87 is particularly interesting because it's rubidium that is decaying into strontium 87 and leaving this, because it has such a long half-life, over these years, it is depending on the rock age where actually this kind of ratio we can find. And this, where the strontium is going to be weathered from the rock, being put into the soil, getting into the groundwater, and then picked up by plants and eaten or these plants being eaten by animals, and therefore it's getting into the food chains. Therefore, depending on where this ends up being substituted or substituting calcium in bones and teeth, it can give us information about where a person spent maybe the last years, if it's in bones, because in bones the strontium is being replaced regularly, and otherwise in dental animal, it's being there for life. So we can tell maybe where this person grew up, where it was born, where it grew up, and maybe where it later died, and we can decide if it actually died at the place where it grew up. That is the simple way of understanding how strontium isotope mapping works. We've seen already it's based on geological maps mainly. There are some other issues that come with it, particularly, as Jane already said, the issue that actually the geologic strontium ratio is different to the the animal and plant ratio. So it has to be these maps that have been created by Bataille already in 2012 that we are using, show mainly geology, but also some age related, rock age related differences. Particularly easy, you can see it at the volcanic arc here of the Lesser Antilles, as one of the islands of Guadeloupe. Here you see the difference of the limestone platform geology and the volcanic arc that divides the island in two. Therefore, you will see in one of the examples the problem that we have with these particularly small islands. And this is then the resulting map. You notice there's quite a strong differences in data on the mainland. We have some very old parts here in the south. That is the Guyana Shield, and then we have these differences due to the volcanic arc and the limestone platforms. And when you, of course, you can divide this map easily into different regions, as we saw already about Britain. So we have the possibility to exclude certain areas where a person could have come from. And one of the examples that we had was a jaguar tooth, which came from Puerto Rico. And oops, this shouldn't happen. Okay, now it worked. The jaguar tooth, which came from Puerto Rico, we know that there weren't any jaguars in this region. So we can exclude actually the islands that it came from. It had a very high strontium value, and you notice when we exclude everything that is not within this range, the error range, we can pretty much tell that the jaguar pendant has been transported somehow to Puerto Rico, probably from the mainland of South America. Then to narrow down the area, we tried again, as we saw also before, to use a different isotope. And that is here, we've been using oxygen. And oxygen has been created by the, or this oxygen map has been created by the International Nuclear Association. And it is, compared to the strontium map, a lot less lesser resolution. But it still might help us if we consider one tooth to narrow down the area by excluding some of the areas within the Caribbean. And so here again, regarding oxygen, we have this differences in the map. You can notice, which is we have particular higher values in the north and the south, so in the higher and lower latitudes, and also it depends on the altitude of the of where the water was dropped on the continent. And because we received point data, the map was transferred into or interpolated to our needs, and we had, in addition to this to these values that we actually had, an error map, and the error map we noticed actually is quite significantly different. So some areas have been regarded as better tested, and other areas less. So we wanted to get this map as well into our calculations. So this is the final map that comes out, and we needed to transform, as we said already, the data as well into bioavailable or animal data, the teeth data. So our values are actually changing to now 22 to 30 here. And we just learned it's going to be pretty difficult to use this oxygen. And we see maybe also why this is so difficult at the examples that I'm showing you now. So actually, this looks all complicated. It's not pretty. It's not very complicated. It's just a map showing that what we need to do is using the rather clear strontium value plus its errors, and the oxygen value plus the errors of the value plus the errors of the map. And therefore, if we compare these two, we are receiving potential overlaps where these regions can tell us maybe, or where we can exclude areas that this tooth is not going to come from. So one of the examples, again, a rather popular example, because we knew this head could probably very likely not come from Cuba, since it had these cranial deformations, and it was found on a Cuban soil in a early colonial cemetery. And if we just exclude or use the strontium data, we are seeing that Cuba is actually quite prominently on the map. But once we put the oxygen in, we notice that we can exclude Cuba and large parts of the Caribbean, and the region that we are looking at, if we use both, is mostly, well, areas where we would expect Mayans to have lived, somewhere in the highlands, actually the Yucatan Peninsula is also just white, but in the highlands of Guatemala, for example, we see very strong results. So we thought, oh great, this is actually a method that works. So we used recently a number of new samples that have been taken, and these are all samples that are modern, because we thought, well, if we actually exactly know the origin of this tooth, where this person has grown up, and these are early either baby tooth or we know that they spent their adolescence at this place, and we thought, well, this should work out quite fine. Unfortunately, we don't have oxygen for some of these, as these teeth were, I think, destroyed after they were tested for oxygen, so we couldn't actually have tested them again. So I go quickly through these examples, and you saw what we've been doing. So now in yellow, you're seeing the strontium results. And here, Cucuta is the place down here between the border of Venezuela and Colombia. And you notice with the strontium data that it actually does exclude large parts of the map. But again, our sample is not showing its origin exactly, but we are considering these areas, the highlands here of Colombia, that we are in close space there. If we take Curaçao, Willemstad, Curaçao, here this sign down here is going to be down here, and we notice that again we can exclude large parts of the map, but we have an issue with these islands that actually the mainland is responding much better on these results. Same for Kralendijk in Bonaire, another island of the Dutch Antilles down here, where again our results are quite indefinite, to say the least here. Or another tooth from one of these islands, Aruba, Bonaire, or Curaçao, which are here, where we have the same issue again, that actually we can't define the island itself. One of the reasons that have been that we come up with is that that seawater is actually influencing the strontium data, and therefore is actually higher than the values that these islands present us. Quite good results we got on the tooth from Santo Domingo, and you notice here, and now everything is just put over. You see the overlap in red, overlap of strontium and oxygen, and we are rather close to the mountainous area in the Dominican Republic and Haiti. Again, if I zoom in, we are unfortunately, again, we don't have the exact spot. Santo Domingo is not highlighted. So what is the issue that we have, that we are never, even though the person grew up here, is not connected to the results, or it's not in the overlapping area of these results? Well, one issue that we probably have is these were rather young people, and young, I mean, or they are still young, so they've been within the last 10 years, born within the last 10 years. And the issue that we are facing is probably that has been so much like transfer of food in the global food market coming to these islands, particularly also when we go to Guadeloupe, which is the next one. And you notice again, we don't even get an oxygen value of this measurements anywhere in the Lesser Antilles of this person. So that our strontium is working, but the oxygen is not. So the water is being brought into these islands, particularly for babies, for pregnant women. The people are not drinking their own water, you could say, or eating their food, because baby food is coming from abroad, from France, particularly regarding the French Antilles. So we really have an issue. You notice if we are talking about modern samples, this last sample that I'm showing you is down here in Caracas, Venezuela, and this was our first try in this earlier paper, where we were like, wow, spot on, we are getting this area covered, and pretty much the only region within the Antilles, within the Caribbean, where this is actually coming up. So we thought that modern teeth are actually a lot clearer than ancient teeth. And then we noticed this is not the case. We have an issue with it, and we tried. Now we had these overlapping cases. I don't know how much time I have left. Okay, then I'm going to be quick. And we looked at biology papers and thought, what about not using this overlapping approach, but trying a probabilistic approach, a likelihood approach? Looking at migration of birds, they've done it here in the Wanda paper on hydrogen, trying to figure out where the birds survived in the winter. Another paper a bit later here from Veen et al. Was using different isotopes, hydrogen, carbon, nitrogen, and trying to figure out where these two types of species actually overlapped and created this hybrid. And from this, we used a very nice function on the bivariate probability density function to do the same with our samples, to first use strontium, then use oxygen, and then using this function to get a probabilistic result on this, regarding the person from Caracas. And you notice, I mean, here we are integrating all the errors in a probabilistic way. So we are getting, I would say, a slightly more realistic interpretation of these results. But at the same time, we in the end, of course, the value is not going to change. So we have still the same issue that using that for areas where these do not overlap. And then to finish up, because I was asked to bring this up, I mean, what we do need is firstly, and you see that at the paper by Bataille, a recent paper that shows all the data they put in for Western and Central Europe. Apparently, Britain provided data, Denmark, but we see, like, for example, the gap here in Germany, that getting samples from certain countries is a problem if or when we are looking at over-regional issues. And Bataille has been working well, over the last 10 years at least, building these maps and then extrapolating the data into even, and there was a whole recent publications that came out to this topic, extrapolating it to US issues, French, and then creating global maps. But the problem that we have there, of course, is that this interpolation is really problematic on getting well, specific origins or trying to figure that out, because we really have often very limited samples of particular isotopes. So the question is, can we firstly narrow down our areas by using more isotopes, or do we actually have an issue with the modern global food industry, and are we failing in that regard, creating these maps for trying to figure out the origin? And then are we back again only on archaeological specimen, which of course here is a particular interest as well. Thank you very much.
Till, thank you very, very much. I thought that meshed very nicely with what Jane said to us. Perhaps one question? Sorry, you can't escape yet? Either from online or from here? Have you got an online one?
No.
You haven't?
Do the floor questions first.
Right. Is there anything from the floor?
I think probably the discussion later.
Yeah, when we all come together
very...
as a discussion, we'll do it like that. Okay. Well, I'll pass over. We'll pass over to Gary Yukang Hao Su, who's from the German Mining Museum, the Deutsches Bergbau Museum in Bochum, and he's going to talk to us about Globalid, a fair lead isotope database. Gary.
This is a folder. Gary, yes. The PowerPoint. There's a microphone. Hello. Hi. I'm very honored to be here, and this seems like 2 years I never traveled abroad, so I'll be a little bit kind of scared because I've been now getting used to the online, very much getting into online conference, so I can feel comfortable here. So I'm kind of taking this talk very seriously now. So I'm talking about actually is an initiative. It's not a funded project. So this led by the Sabina Klei is she's my boss, and so we have the team with Thomas Rosa, Katrin Westerner. So we together, during the pandemic, because we couldn't travel a lot and they couldn't actually produce a lot of sample because the COVID. So we come out kind of digest the late isotope data we have, and so that's where we started these things. Since 2019, I published a paper on Chinese late isotope data from Chinese old deposits. And so then we sit together, so how can we organize this database on a global scale? And that's how we come up with this idea to build out a digital platform and also digitalization of the late isotope database on a global scale. So basically, I'm talking about today is not particularly like answering some particular research question. It's more like a tool we developed to apply for the database, isotopic database of that. So currently, I'm talking about specific for late isotope data, which we use as in particularly archaeometallurgy, also archaeological science. We don't have, most of the time, we try to, if we produce some kind of sample, the first things we have to do is to go through the very tedious search of reference data. So because there are wider scale in different publication, and second step, we have to interpret all what that means, because people have different habit to organize data. We have to interpret it in our own way. And so then certainly we have restriction because of language barrier and because we don't have access to the particular publication in the past. So sometimes it's very difficult to give a comprehensive understanding what kind of data have been published. So that's the reason. That's the current state of the late isotope data in archaeological science. So during a preparation of our project, there's another team in Spain. They also focus on this to develop this kind of digital platform from the Iberia Peninsula. So there's in the website. They also produce this kind of digital platform, particularly for the region. And so that's the reason we thinking about the current state is not fair principle, which means like, I just give you an example how usually look the database we talk about. So Oxley is a database produced in Oxford 20 years ago. So it's probably most cited late isotope database for the archaeology. So that's the data table. You can see the first line, and Iberia is another thing I just mentioned, and also the Killick in Arizona. Also, he collect a global scale of database. He also published paper on it, and that's the last one is the paper I published on Chinese database. You see, we use different terminology, and we care about probably different parameters about the database. So that's the difficulty when people come to this database. Okay, everybody have their own habit to do their own things. That's the really difficulty of using the late isotope database on a very organized way. And so our aim particularly is to develop a community standard, which is to reporting and publishing the late isotope data. And the second one is construct a digital platform people can retrieve, we can access, and also can contribute, visualize, compare, and share the database. And the aim is, of course, to reduce the work. We as a researcher, we don't need to, after work, we don't need to every time to search the database. We need to try to reproduce the database. So finally, we hopefully can achieve this very principle: findable, accessible, interoperable, and reusable. So right now is the current workflow we come up with is like we currently are the core team, so like 4 of us. We will particularly manage data, so we hope the community can contribute the data to us, and we will help to check in and investigate, examine the information we receive, and then we actually host our database in our institute. So there will be a lifelong hosting unless we got broken. Otherwise, we're lifelong hosting, so there is no problem with like some type project ended. The website or some project cannot be maintain. So then the user can use just internet, mostly like your browser, and you can have access to the data. So that's the roadmap on the right hand side. So now, so that's the basically the current workflow we have. And let's talk about the database and what we have right now. So right now we have first of all, we have to kind of investigation what kind of database already available globally. So that's the coverage of database we look at. Right now, the whole database have like 20,000, around more than 20,000 entries. But the core one, so in the website we're going to present later, we only have 2,477 because we are not just put the data online, we have to check to validate all the information. So there's a lot of work. So we only mostly publish the data from Near East and Europe, which is the red dots. But you can see other database, we are already in our database, but we have lack of time and the expert to actually complete all the checking. So that's the current state of the data coverage we have. And the data structure we right now we have can be divided to 5 sections. So one is the geographical information, and the second one geological information, and also the sample, and all the data we have. Reference also very important, so we try to provide the full reference or DOI to people we are interested to know more about data. Also, the instrument year, which can be expanded. Hopefully, in the future, we like to also include the measurement data, so people can know whether the reliability of the data look at. And the age model is something I think that's very useful for people who are more interested in the geological questions, using the model age and mu and kappa, the uranium-thorium uranium ratio, to try to understand the geological setting of the particular deposit. So that's the data structure we have right now. So the whole database is application was built on the R language in the Shiny app, and so that's totally open source. The beauty of this, like you can see it more like you can adapt, you can develop a very sophisticated plot, and also they are open source, so people can freely to use or to modify according to their needs. So that's basically that's the reason we choose that, and also it's free. That's probably the most convenient reason to use that. And so I will just showcase a little bit about the app we have here. Just take one here. Let's already open it. Only no. That's another one. I will check. Oh, I think. No? Okay. Yeah. And open the web browser. Yes. Oh, yeah. Sorry. Okay. So basically, that's the first page of our app. So there's a map view showing the database right now we have, and on the right side is the plot. You can normally, when you do that, you go to the Explore, and they are showing you 2 plots by default, because they're loading all the database with. And normally, just demonstration, if we like to look at the data from the Greece and Lorient in Greece, and That's it. Okay, that's basically if you know where the region you're interested, you can do the search. And then I just want to show this plotting system for this density plots. So basically, you have to view. Okay, so that's the density plot. So if you try to represent it, you can change the parameter, depends on the percentage of you want. Like here is 99% of the contour plots for the whole field. So basically, you can apply to the same plot down over here. So I don't need to repeat that. And then you can also change it to, you want to look at only the 3-dimensional or 2-dimensional plots. Interactive. So that's the 1-dimensional plot. If you're interested in only 1 dimension, you can do that. And you have the 3-dimensional function as well. That's the 208, 207. 3D scatter. Yeah, that's the 3-dimensional plot. So basically, once you finish, when you're satisfied with all the plots, and then you can download not just the plots itself. Here you can download the plots, also the database, which is the Lorient data I showed. And another feature I would like to mention is you can upload your data, but I need to verify I'm human first. That's the one. But yes. And sorry, yes. The good thing about this website, so you can immediately plot your data onto on the plots, so you can see how they fit to the database. For example, I will just give you an example to show that here. Right now, it's very simple. Okay. Also, that's very simple data. So you have simple then you have a group, you have a latitude, longitude, and also the 3 isotope ratio. And then you can just upload it here. Here example data. Okay, here we go. So they not only showed you the data you have, they also calculate, as you see, they calculate the model age or also all other parameters for you. And so if people don't need to use the plotting function, they can only use this tool to convert their isotope value to the model age or other value they want. Then we go to explore, they will show up here. So I probably do it 2D is better. So that's it. Yeah. So that's it. So that you can see that's the very the convenient way to quickly check how your data fit into the old field. You whether fit the old field or you want to choose another old field to see how they compare to other data sets. And that's another things like the resource function here. All these are written in R language, so they can be list all the R script. They can be downloaded, and people can use them they use it and modify it. And I think that's the very convenient thing to do that. And everything we got here is also on the GitHub, which I will show you later. And I come back to my slide here. So I just try to repeat or try to emphasize how the globally it will be, or we are aiming for is a fair long-term project. So feasible. So hopefully each database will find a DOI. So we easy also later on we like to find a unique identified resource number, so people can actually use this number to track track this particular database or data interest. And the second one, accessible, so there's no restriction. As you see, the source code also available for the further development. And interpretable, so data encoded in this UTS file, that means we can also use, depends on, it doesn't regard this of different language, maybe Chinese, Russian, different later, they can be all, can be integrated or integrate into the database. Then also the most important thing is sustainable, because it's not a funding project. It's a benefit of it is like we don't attach to the money, so hopefully we just attach the passion. we like to maintain the database. So hopefully that's the thing we want to do. Like there could be a global, globally can be a continuation of project. People can be run for a long run. And I will just show you the list, the not list. I show you this. Okay, so that's the resource we have. We have the email address, which people can email us the contributed database and which you like to put on the global aid. And we also have the data repository. We store our data. And the web app I already showed, and also we publish article on archaeometries about how this new development of global aid. And we also have the source code host in the GitHub repository, so people can just download it. And ResearchGate will have our introduction of our project. And the next step, we just do an advertisement here in February 8 to 10. We are planning to have a workshop, which would like to address some very important questions concerning the global late isotope data. First of all, we like to know which data and metadata information is crucial, because right now we are at very beginning of the stage, because we are actually still inventing some thesaurus terms for our own use. So maybe our terms not agreed by other teams. So that's the reason we wish to have this project workshop and to find a standardized way we can report the isotopic data. And also there's another important issue is visualization, because as you see, the tool mostly is about the plotting. So we are thinking about how can we report isotope in not just one way, multiple ways. So we kind of more like comprehensive way to present the data. So that's why in recent years, they quite a lot of paper, they actually do a lot of plotting, like Isoscapes is one, and also like a three-dimensional ternary diagram. We also have the mixing model for the late isotope data. So that's a lot of variety now going on. So that's the reason we hopefully there's a one way, use this workshop, this opportunity, we can discuss how visualization could be important, could be useful to be incorporated in this web application. So that's how we had it, and hopefully it could be will take place, and hopefully there's many can be joining us and to make a better accessible or findable to make a database which can be used and can be sustainable for a long run. Thank you.
Thank you very much. Yeah. I thought that was very exciting, and let's hope that it does take off, and we shall all see in February, of course. Are there any questions or points immediately? Yes.
To do density for so long. I'm so excited about this. I have so many lead isotope data from Roman populations across Europe, which I can just slot into that. It's great.
I think many of us have wasted a lot of our lives scanning and OCRing and creating our own spreadsheets and things. So yes.
Thank you.
Sorry, Gilberto, yeah.
Are you doing 3D kernels right now, or are you planning to do that?
Right now, only the scatter plots.
just scatter plot, and the density is just bidimensional that you're doing?
Yes, density plus two-dimensional.
Are you planning to implement, you know, a little bit more sophisticated, like kernel density in 3D or things like that?
Yes.
Right.
Personally, for example, I use a ternary diagram, and yes, that's why the workshop is like, I know we are not alone, some other team also develop some method. We like to, so we all have our method, but I try to find a way to incorporate everyone's effort and to be able to access to others users.
And the final thing is, you mentioned some, you know, expertise in critically analyzing the data that gets into the database. Can you tell me a little bit more about the checking that you're doing?
Oh yes. For example, for example, for my Chinese database, I publish paper on that, so I just go to the Chinese literature or deposits. So for my Chinese side, so in this project, I'm more focused on more data from Asia. So we have other colleague who works in, for example, the Catherine Western working in the Kosovo. So she's responsible for that region. So we have some people who are only know that regions. So that's why we database totally have like over 20,000, but we only put 2,000 live because we are limited knowledge to check all these things. So we only check on 2,000 data sets. So it's not everything's on our disk, but we cannot publish because we are not confident about the data we have.
You're checking the quality, the origin.
Yeah, we are checking the integrity of data, which means what kind of data they see. So we try to honestly reflect what the data we have. So sometimes it's impossible to check because they never publish, for example, the analytical procedure. So sometimes they only have data. So that's the data, and we have to understand. Okay, there's no more information we can offer, but we can make a note something. Okay, there's no this data is not available at the moment. But that's the one for measurement data. The other one for the deposits, like which require just not for the paper, we have required to go to the geological background to check which deposit you're talking about and how can we categorize the deposit.
Yeah, that's exactly what I meant. I mean, are you, for example, checking each data for the model age and check if it's confidently, you know, fitting with the geological models that you have?
Oh, yes.
And throwing outside the outliers or not?
Oh, yeah, no. I think we are checking geological, like a basic information, what kind of oil they produce, what kind of deposit type they have, geological age, which report in the oil deposit. But the model age is separate thing. Model age is the ideally late growth model produced by the different models. So they are quite different. Yeah.
I think we need to move on,
Yes.
but clearly we're going to come back to this in the discussion. Has there been anything from online?
No, nothing.
Okay, not yet. Okay. Well, the last paper this morning is a view from a different discipline, but we thought it was very, very important to hear about the experience of databases and data sharing in the world of genetics. So Mark Joblin, who's from the School of Genetics in the University of Leicester, is going to talk to us about past human population migrations, lessons from genomes, ancient and modern. Over to you, Mark.
Okay, thank you very much, and thanks for the invitation to speak here today. So, as has just been said, I'm a bit of an outlier, being a geneticist, and I agreed to give this talk about 3 years ago, and much has changed, excuse me, including my cough, including our own research. So actually, we're working much more in animal genomes now than we were when I was first asked to give this. So I apologize for hogging my throat. The talk I'm going to give is about this title, which was, I think, given to me. I can't remember whether Steve dreamt it up or I did. But what I thought I'd do is give you a bit of context about genetics, talk a bit about how we look at modern genomes and some of the issues around that in terms of inferring the past and inferring who migrated and from where and when. And then also to look at the very important area of ancient DNA, which is an area that I've never worked in, but I'm going to tell you something about that, and how that's really transformed the landscape of how we understand the past. And I'll try and bring in, since this is an isotopes meeting, some analogies with isotopes and a few examples where those two things have come together. And one of the take-home messages is, I don't think isotopes and genetics come together enough, and there needs to be more done to integrate these fields. So we're talking about DNA, and DNA has 4 letters, which are given here, but sometimes written H, Y, P, and E, as Steve Jones has said, because there's a lot of hype around DNA, and there always has been in terms of what it can deliver. I think the new generation sequencing methods are actually delivering on some of the hype that used today. So it's worth thinking about the scale of the data, because the human genome is a big thing. This is the human genome. Some of my colleagues with the books printed out of one haploid genome. Each color is a chromosome. And we take that around, around to public engagement events, and also frighten medical geneticists with it. And this is one page which is printed font size 4. It has 43,000 letters on a page. It's double-sided. Each volume has 300 pages, and there are 130 volumes. So genomic data is big data. The human genome is quite a big place. And one of the things that it contains, other than things that are medically relevant to us, is information about the past. So we can look at DNA passing to us from our ancestors as a message from the past. And the challenge is to understand what that message means. So we have points of variation in the genome. We have modern population samples that we can collect, sometimes more easily than others. We can sequence those genomes today using modern sequencing technologies. It's possible for you to get your own genome sequenced by a commercial company for about $800 to a high degree of accuracy these days. Then we need models and analysis to say, what does the variation mean and how can we interpret it in terms of the past? And as I said earlier, the big thing that's come along recently, really, is the analysis of ancient DNA. The ancient DNA world started quite a long time ago. It started back in the 90s. But almost all of those results published in front pages of Science and Nature are wrong. They're all wrong because it was basically contaminants that were being sequenced. And this new technology, as I've explained, has changed the game now. So the results are no longer wrong. So the variation we're talking about here is just one kind of many kinds of genetic variation. And it's single nucleotide polymorphism. So the change of one base for another in the genome. And we have lots of other kinds of variants which are important in health and important in evolution and important in genome function. But essentially, nearly all of the ancient DNA stuff and the modern DNA stuff you see in this field is about SNPs. So our genomes in this room were 99.9% similar to each other wherever we come from in the world. But each of our genomes contains 4 to 5 million SNPs, and that's what we're really talking about. Out of the 3,200 million bases, we're talking about the 0.1% of variation that exists among humans. And it's a question of interpreting what that means. So there are different components to our genomes which are inherited in different ways. So my career started out working on the Y chromosome over there on the left, which is the male-specific chromosome that defines maleness in mammals. And that passes from fathers to sons. And then there's a complementary piece, the mitochondrial DNA, which passes from mothers to children. So those two tell us something interesting about the past, which is differences in male and female behavior. And in humans, that's an interesting story, which I'm not going to talk about today. And then 98% of our genome that's left is the autosomes. And these are the chromosomes that come to us from both parents. So while Y chromosomes and mitochondrial DNA have specific uses, for example, in the Richard III identification case, most of the information is gained from the rest of the genome. So what I'm going to talk about here is just whole genome sequencing, which is taking DNA from one of you, for example, and just sequencing everything. You get the Y chromosome, you get mitochondrial DNA. If you're a male, that is, you get a Y chromosome. But you get everything else. And then the process of inference is really taking the whole genome as a whole. So let's start with modern DNA samples. And there are good global DNA sample collections available that you can purchase. So you can get hold of these DNAs if you want them from central repositories. They come from individuals around the world. So for example, here we have the 1,000 Genomes Project DNA samples. And there is some metadata, so we know what the population is called and where it's from, but that's it. So often the metadata associated with these kinds of sample sets is actually very poor. And these have been analyzed. This is based on whole genome sequence data here. And this is an example of a structure plot where what we have here is about 2,500 genomes, and each one is a very thin vertical line, such that you can't actually see individual genomes. But they're colored according to a number of clusters that are identified in the data. So the method here identifies the best NK clusters within the data, and then post facto assigns those to populations. What you see is that each population labeled here has a distinctive palette of colors, and these are the Africans, breaking down into two clusters. For example, these are the Europeans, South Asians, and East Asians. So in other words, without knowing anything bad about the samples beforehand, a clustering approach can assign individuals to populations reliably. There is population structure in human populations. So that's all very well, but how do we infer the past from those patterns? And actually it turns out to be a very difficult thing, an unreliable thing to do. So the big picture here is the out of Africa migration and then subsequent admixture, reshaping variation post facto. And other than that, it's not really telling us very much about migration. One important point I just want to mention is that there's an ethical issue these days with whole genome sequencing because all these samples were given anonymously. That was the condition of donation. But now, thanks to open source databases, it's possible to identify those individuals and work out who they are. So if any of you have given your DNA or your samples to UK Biobank, for example, you're actually vulnerable to being identified by a third party today. And this has thrown the cat among the pigeons in terms of modern sample sets. This is an example closer to home. So that was a global set. This is a modern DNA set from the United Kingdom. This is the so-called People of the British Isles project from Oxford and Walter Bodmer. So these samples are very carefully recruited for individuals who have all four grandparents born within an 80-kilometer radius in a rural location. So they're a very atypical sample set. And again, what's happening here is population structuring, pictured here as these colors. So after the analysis, everyone is given a cluster, which is a colored symbol, and then plonked in the centroid of their grandparental birthplaces. And lo and behold, you get population structure, including things like differentiation of Cornwall and Devon. So the program didn't know these individuals came from there before, but after the analysis, it can distinguish those two groups, for example. Interpreting what this means, again, is hard. So in the paper, they interpret this big red cluster covering central and eastern England as Anglo-Saxon mass migration. But if you look at the data in the paper, actually, there are other alternative explanations, and you can't exclude other explanations, other migratory explanations for this kind of pattern. This kind of thing is applied at the individual level these days. So if you get your DNA tested by living DNA, they will assign you to these clusters as an individual and tell you where your ancestors came from at the level of sub-regions within Britain. So that's at the population level. What can we say about migration from these kinds of data? Well, that is focused on particular groups. So this is the example of the European Romany, so 8 million people spread across Europe, originating in a diaspora where the linguistic evidence places the source somewhere in northern India and the timescale around 1,000 years ago. And here we have an example of a structure plot, as I showed you before. The European Romany and European non-Romany are different. You can see they have this blue component in the cluster, which is at its highest frequency in India. And they're very distinct by the time you break down the sample set into 5 clusters. So this strongly supports the idea that there is an Indian affiliation or origin for this group, that the groups are very similar despite their geographical range. So culture has kept them homogeneous despite being widely spread. They're very distinct from their host populations. And again, this kind of approach of analyzing ancestry can be done at the individual level as well as the population level. For example, in direct. Let's move to ancient genomes, and what's really changed is next generation sequencing since the bad old days back in the 1990s. Samples are still biased because there are some regions where it's just hard to get samples from and hard to get DNA. The new technologies have revolutionized the field, and very small DNA fragments, down as small as 25 base pairs now, can be sequenced. And that's below 50 base pairs is where most of the DNA is in old samples. So these methods can get those bits, which couldn't be got before. And one nice feature is that the technology gives you so-called damage signatures. So you can tell from the sequences which pieces of DNA are old ones and which are modern contaminants on the basis of how damaged they are. And the development of understanding that the petrous bone, which is inside the inner ear really, is the best place to get high endogenous DNA content has also made a huge difference. So this cover is from Cell in 1997 based on the mitochondrial DNA analysis, which says very boldly Neanderthals were not our ancestors. And actually it's wrong, because now we know that they are, because we've got whole genome sequences. And how far back can this go? Well, I think it was last year we had mammoth teeth from permafrost back to 1.65 million years with whole genome sequences. So in principle, you can go back beyond 1 million years. There are no human DNA sequences that old, but it's pretty old. So here's an example from the British Isles where, again, we're looking, as with the Romani, at people out of place. So the Romani are, if you like, an Indian population in Europe. This is an example from Martiniano's et al.'s paper from a cemetery in York, a Roman era cemetery, where you've got individuals with the same burial practices, but based on the genome. So this is a principal component analysis of the genomes. Here are most of the burial individuals up in this European cluster. There's one individual out here in the Middle East, so clustering with modern populations who originate from they're Palestinian, Jordanian, and Syrian. So it looks like this Roman era individual, the ancestry of this person was in the Middle East. And based on the stable isotope data and the same sample set, which is unusual to see still, that supports an ancestry and childhood of this individual in the Middle East. But it's not possible to make a more precise definition of where exactly that was based on these kinds of data. So this individual was born there, migrated to England, and died in York, was buried there in the same way as people who show continuity in their genomes and their isotopes with the local environment. This is the structure plot, and this individual here, you can just see, that's the anomalous individual whose genome, based on this clustering approach, looks much more like a Middle Eastern genome. A lot of the narratives in ancient DNA papers are around this idea of continuity versus replacement. And that we see that at all kinds of levels in genetics. We see it at the level of multi-regional evolution versus the out of Africa hypothesis, which was something that's now not really talked about so much. We see it in the idea of acculturation versus denic diffusion in the spread of agriculture based on Cavalli Sforza's work and subsequent challenges to that. And then we see it in the Anglo-Saxon mass migration versus a cultural shift not accompanied by mass migration. So it's a recurring theme. This idea is, do we have continuity and just cultural evolution, or do we have new folks coming in, killing everybody or eliminating them somehow and imposing their stuff? All of this is very politically charged. For example, the British National Party used very flawed science to support the idea of continuity within Britain. And that's radically changed now we have ancient DNA data. So here's just a couple of examples of papers, and most ancient DNA papers have titles like this these days, revealing lack of continuity or continuity. That seems to be the major narrative. So one of the major discontinuities that's pretty clear from the ancient DNA data is one associated with technological change in the Bronze Age, which brings in a massive migration of a so-called step ancestry component, which matches individuals who are found in the Yamnaya region of the steppe from about 4,500 years ago. So this ancestry spreads across Europe, as described in these papers, and ends up as far west as Ireland. So in sites in Ireland, there are individuals who have high levels of ancestry tracing to matching the Yamnaya and tracing to the steppe. Here's an example of a Yamnaya burial from near Samara in Russia. And here's an example of some of the kit and associated tech that, in my simplistic view, I see as associated with these kinds of this culture and the change that it brought. So just to give you an example of this replacement, this is the bell beaker phenomenon in Western and Central Europe, where you see a replacement of styles, ceramic styles, and it was a short-lived replacement, according to these accounts. And the analysis being done here is from 400 Neolithic, Copper Age, and Bronze Age Europeans, including more than half of them associated with beaker complex artifacts. And what we have here on the left in the dark sectors of these pie charts is the proportion of steppe ancestry. So this is the proportion of ancestry in these different sites that can be matched to the steppe originating populations. You can see that it's very high here. And that ancestry temporarily shifts across the beaker cultural transition. So prior to the beaker cultural transition, it's very low. After the beaker transition, it's very high. So there was a big input during this short period of time. And this shows Y chromosomes through time. This is time from the distant past here. That's the Neolithic. This is Copper and Early Bronze Age. And the color means the type of Y chromosome. So there's a shift from a Y chromosome known as I2A here, which was fixed prior to this transition. And then it switches almost entirely in a very short period of time to a completely different Y chromosome type, which is the common type of Western Europe today. So this switch occurred associated with this transition. Males essentially look like they were replaced during this time. The conclusion of this paper based for Britain is that there was 90% local population turnover by the mid-Bronze Age. Most British post-beaker DNA comes from ancestors in Europe who are actually, signs the wrong way around, more recent than 4,450 years. So the time scale this happened over is several lifetimes. Will you find individuals whose isotopes tell you about this? I don't know. Since there was Vikings in the title, I'll just refer briefly to this paper, Population Genomics of the Viking World. 442 ancient genomes across Europe and Greenland. And essentially, the story in this paper confirms kind of what we thought, which is that there's input from Denmark into England, Sweden into the Baltic, and Norway into Iceland, Ireland, and Greenland. And a lot of cosmopolitan input into Scandinavia. So the Viking world is drawing ancestry into Scandinavia from around the rest of Europe and beyond. There's also the detection of kin. So, for example, 4 brothers in one ship burial and widely separated second-degree kin like cousins. Cousins, one in Denmark and one in Oxford. So that's very interesting to see. It's another thing DNA can do. It can find kin either in grave sites or in a more dispersed way. The stable isotope analysis is described in this paper, but it's not really systematically analysed as far as I can see, and I think that's a missed opportunity. Can we bring ancient DNA together? This one of the things around this meeting is thinking about fair data. And one of the big problems is these guys hate each other. And they always, if they put a grant or a paper to review, they exclude reviewers and they're all the other guys. So there's a lot of testosterone swishing about, and it's led to some very unfortunate things, which I won't go into. David Reich makes his data sets publicly available quite well on his website. But I think the promise and the hope for the future is the new generation of young scientists, some of whom have been trained by these guys, who are moving towards shareable and interoperable data with metadata standards. And they have this forum called SPAN, and they have meetings, and they're putting together toolkits for metagenomic sharing. And the metagenome approach really is thinking beyond the human genome. The associated genomes, for example, in things like dental calculus, which can tell us about dietary change, the oral microbiome, pathogens, for example, Yersinia pestis, which is recoverable from tooth pulp, and putting those even together with other signals of migration that come from animal. This is the example of red deer, where there's good evidence from ancient DNA that actually red deer were transported by people over long distances. So the Scottish red deer, phylogeographically, shouldn't be where they are. They're actually migrants. The deer are migrating as people are taking them. So there's a lot of promise of bringing all of these things together. There's work to be done. There are biases, there are ethical issues in the ancient DNA world as well as the modern DNA world. There's certainly a need for fair principles to be enacted. And there's a need for better integration. Thanks.
Thank you, Mark, for that. Are there any questions? Sorry, should we have Till first, or we'll do Gilberto first? No, go on, Gil. You go first.
It's me? Yeah. All right. We've been looking at the recrystallization of the petrous and the teeth, because these are the most common bones that you are using for DNA. And of course, I don't understand anything of what you said, but thanks for the last presentation, because it was very clear. And they tell me, and we tested the recrystallization of the apatite versus the endogenous DNA that they were extracting. I will not tell you who, without they, and some of those that they mentioned. And sometimes we see high recrystallization, and they tell me, "Oh, this is very good DNA." Sometimes we see almost pristine apatite, and they said that we cannot extract anything. Everything we extract is junk. I would like to understand a little bit better this control of the endogenous DNA versus whatever you extract from the bones.
Yes. Well, as I said at the beginning, I don't do ancient DNA work, so I'm just just telling you what I know. I mean, it's very much an empirical thing with skeletal remains and DNA recovery, as far as I can see. I mean, if there's a petrous, they'll use the petrous, whether from a human or an animal source. And in the paper where I showed a figure where the skull is coloured, they actually took skulls apart and recovered DNA from different tissues and just found that empirically the petrous was the best. And it is, a good petrous will give you DNA quality nearly as good as a modern genome, even though it's several thousand years ago. How that connects to crystallization, I'm not really qualified to say.
I was surprised because, sometimes from an organic point of view, I see that there is almost no pristine apatite. And they say, oh, this was great. And sometimes there is something that I would say like almost a modern one. And they say, no, we can extract anything. So that means that there are a lot of factors, biogenic alteration, and this has absolutely no relation with age. So there is modern bones or almost modern bones, which is totally degraded, and very ancient one, which is very good. So we are looking from the inorganic part, but I cannot correlate it very well with what they say they can extract.
Okay. Yeah, that's interesting, but I can't answer why that is.
Phil, it's over to you. You seem to have brought Caribbean music along with your Caribbean paper.
There's a party out there, yes. I was wondering when you were talking about the replacement of population or replacement of people, can you tell from the DNA as well how many? I mean, considering you're studying individuals, but is there a possibility to actually look at the number of people that have been living there and that have been replaced based on the individual DNA structure?
Well, yes. I mean, there is a kind of another effort out there, which I haven't really talked about, which is to do with modeling approaches that model the numbers of genomes coming in and things like reproductive success, and also do that in a spatially explicit way. So it's tricky, and there's a lot of debate going on about it, but certainly, I mean, models, approximate Bayesian computation models, which are really based around summary statistics, have been doing that for a while. So you can come up with a number of scenarios involving different numbers of migrants, different numbers of back migrants as well. And you can exclude models so that you can say, well, it definitely wasn't this, 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 and this, but quite often you end up with equiprobable models left, so you can't really say which is which. So for sure, there are methods, and there are new methods coming out which are spatially explicit and incorporate things like effective population size, reproductive reproductive success, and so forth. So I think there's more work to be done on those. There's people who disagree strongly with each other in those fields, I'm afraid, but that's life. So yeah.
Right, I've been a rubbish chairman, and we haven't really got a lot of time for discussion now, but we will have a big discussion at the end. So we're going to move straight to the poster presentations before we go to lunch. But I would encourage people to grab the speakers whose papers they were interested in over lunch and ask questions. I shall certainly be doing that. So Charles, over to you.
Could I ask,
do a better job than me.
could I ask the poster authors to come up, because you're going to have just a few minutes before we release people for their lunch. Could I, the poster authors, 1, 2, 3 of you plus myself, you're welcome to try and lobby during the lunch interval for who's going to get the prize, but I have to say it's already been decided, and Steve will be issuing it immediately after we come back from our lunch, which I think is 1:20, 13:20. Right. Gary is in the row and just going to start putting up the slides. There we go. Who's first up? Just really, all I want to do is just that you can put a face to the poster and just say who you are, 1 or 2 key lines. There are, beside each of the posters, there is an abstract, which you're welcome to take a copy and take away with you. Over to you. Oh, you were?
Sorry, which one is yours?
Yes.
Yes, that was the one.
Or should I just speak with this?
Yes, stand at the fact.
It was this one.
Yes. Thank you very much. Okay. Well, hi, everyone. I'm Madeline Bleasdale, and this is my poster, Reconstructing Cross-Channel Connectivity in Later Prehistoric Kent Using DNA and Isotope Analysis. So we've touched on many aspects of this already today, and it's very nice to hear people saying, oh, we got to combine DNA and isotopes, which is definitely true and definitely challenging. So obviously we've been looking at mobility for a long time between Bronze Age and the Iron Age using many different things. So, you know, imported objects, coins, and obviously later in Roman history get textual sources. But now in recent decades, DNA and isotopes has really transformed how we're looking at things. So I am part of the COMIOS project. So this is a big ERC project that's been going to be running for about 4.5 years or so. So a couple of years into that. It's headed by Professor Ian Armitt at the University of York, and it uses osteology, funerary archaeology, ancient DNA, and isotopes to look at connectivity in Iron Age and Bronze Age Britain, looking at these connectivities between the UK and the continent. So I am the isotope postdoc on this project. Now, one of our big outputs so far that COMIOS has been involved in was this very big genetics paper that came out, I think, in December, and it was about 800 genomes were published, so it was a big one. It was led by the team in Harvard, so David Reich, who's already been mentioned, and we were looking at genetic change through time, and we saw this kind of big increase in this European early farm ancestry in the Bronze Age, so you can see that going up in the graph. But part of this, when we looked at this, was also that we saw a number of genetic outliers in Kent. So we decided to kind of go back to a more regional scale and look at... 3 sentences. I'm nearly done. So this is bringing in the isotopes now. So we focus on these 2 sites, and we're hoping to kind of showcase, how the DNA and the isotopes can tie together, or sometimes show maybe contradictory things. And yes, please come and talk to me, and I'll try and do a more succinct job of that in lunch break. But yes, we'll be extending these data sets very soon. Thank you.
Thanks very much, Maddie. Can you pick up the next slide? Not sure who will go. Remember, people are waiting for their lunch, so as quick as you can. 3 sentences, maybe long sentences.
Okay, perfect. Thank you. So, this poster is about some of the results of my postdoctoral work at the INS of Lyon within the RSC project Silver, directed by Francis Albaret. So, in fact, silver played a major role in the monetization of ancient Mediterranean civilization. So here we combine silver isotopes and trace element analysis together with lead isotope data on different galena samples from Spain to assess whether this Iberian galena was actually a major source of silver for Roman Stone Age, because in fact alternative ores have been proposed. The first point is that the very wide range of silver isotopic composition of the galena greatly contrasts with the narrow range of the Roman silver coins, which is centered around 0. That's the first point. Then we can see that the lead isotope and silver isotope composition of the galena are not correlated due to different fractionation process. And even if the lead isotope composition of galena from the Betic Cordillera, so in southeast of Spain, best fit the composition of the coins, the fit for silver isotopes is at best sporadic. So in addition, the positive correlation between antimony and silver led us to suggest that together with antimony, silver derived from hydrothermal fluids of mental origin, which will react with pre-existing galena. And during this interaction, there will be a coupled substitution of silver and antimony instead of lead, and galena will act as a silver sponge or a silver trap. So we have silver-rich galena samples which have a mental silver isotope composition close to 0 and close to the composition of the coins, which was a major source for Roman Silver Stone Age. And in contrast, we have silver-poor galena, which have a composition much more fractionated and which were exploited only for lead, this lead being then used to extract silver from alternative ores. And thank you.
Thank you very much. Can you put up the next slide? You know how to. I'm also failing as a chairman. As the 3-sentence rule clearly is not working, but I'm sure it's very good stuff and well worth the extra time. No, that's mine. That's. Yeah, Byron, you're up. So there are, by the way, a few extra chairs set out at the back. So I'm sorry you're a bit congested at the beginning. But you need space for your laptop when you come back afterwards. If you wanted to spread yourselves a bit, there is a bit more space.
Hi, so I'm Bryony Rogers. I'm a PhD student at Durham and at BGS, working predominantly on strontium isotopes in cattle. So this is a case study from my PhD project looking at high resolution analysis of 8 cows from a site just to the south of Cambridge in the new biomedical campus underneath the AstraZeneca building. So I looked at the M2s, which are formed in cattle between the ages of 1 month and 13 months. So at the start, you also get the strontium signal from the mother's milk because strontium is passed on through the food chain, and then towards the end of the tooth, you will lose that signal as the animal becomes weaned. So the 8 teeth that I looked at from this enclosure, which is a Middle Bronze Age enclosure, and the dates of the cattle I looked at are from about 1545 Cal BC to 1385 Cal BC, obviously with date ranges because it's radiocarbon dated. Of the 8 cows, we see 4 that are in the sort of blue bit up. I don't know if this is in the sort of blue bit. This is the expected range of chalk. We have 4 cows that don't look like they ever leave the chalk, which is the sort of, in my artistic interpretation, as the sort of green band in the middle. We don't know which part of the chalk they came from. The site is on chalk, but the chalk band that the site is on runs all the way from Wiltshire in the south up into Norfolk. So I couldn't tell you if they were local to the site for their whole lives, they moved around the chalk, or they moved once from Wiltshire up to the site. It's probably likely that they are relatively local. We do have 4 individuals that show some evidence either of themselves moving or of their mothers moving. So we have up here we have these 2. One of them moved to the site after the tooth formation, one of them moved to the site right at the end of the tooth formation, and then down here you have these 2 where you have evidence that their mother was moved onto the chalk from an area of probably limestone, sandstone, mudstone, either to the north or south of the chalk. We can't tell because it looks very similar, just before the birth of the cow.
Thank you very much. Could you take that slide? Mark, are you going to talk? Just if you put mine up then. It's the battlefield one.
This one?
Yeah, that's one. Yes. Oh, you're going to. Oh, you will.
It won't be more than 3 seconds.
That's right. That's not that one. Sorry.
No, it's not that one. It's the other, my one. The one that we all wrote together with my name's on. Yeah. Top Isotopes poster Steve. He's the first author.
That's the one.
Control L. This poster, very, very briefly, is just a first report on a pilot study we did combining iron isotopes with lead isotopes with strontium isotopes to try to solve the problem on which many people are working, and particularly Jean Millett, who's here, of provenancing iron material. And we're going to carry on with a collaboration with colleagues in York, Julian Richards, Dawn Headley, in Hull, Peter Haken, and of course with the BGS, and we've some money from NEIC to do that. And Jane here is one of our team. So do look at the poster, but it's very, very preliminary.
Could you put my poster? I'll just see if I can obey the 3-sentence rule. Right, so one of the reasons that I'm involved with this is that I really need the data that you've got, because developing a methodology for finding unknown places, such as battlefields, it works fine when you do look at the literature, you look at the landscape, you can get a very high probability that you found the site, but you then need something to test that. And I have shown that at Fulford, what we have is artifacts, and they have survived in wet conditions, they've survived in plough soil, they have survived in places where they were excavated, and there happens to be a cemetery nearby where they dug some things up. They have survived in anaerobic conditions. So what I'm saying is there is stuff out there to be found. What we need is the science, which will then allow us to provenance this thing and prove a lot of these unknown events. I'm working on 1066 era, and we have a lot of theories. I hope very much that science will eventually be able to prove it. Right. Thank you very much. Thank you very much indeed for your rapt attention. And I declare that it is now lunchtime. We are reassembling here at 13:20.